All right, welcome to topic 9.9. We are starting to kind of wind down the number of gas laws that we have to work through. So at this point, we're going to work on Dalton's law of partial pressure and Graham's law of effusion. For this topic, you're going to definitely need a periodic table, but also you're going to need that formula sheet because we are going to need not only the formulas, but these constants that are down here, and we'll talk more about that here in a moment. So the first thing we're going to look at is Dalton's law of partial pressure. And this first equation is really not, I don't think, anything groundbreaking. So when we look at the total pressure of a gas that is a mixture, so oftentimes like scuba tanks, for example, or as you exhale into a balloon, we say that it's carbon dioxide, but really there's other things in there besides just carbon dioxide. But what we're saying is all the pressure of the individual types of gases combined together into one net or total pressure. And so what we see here is that we have pressure 1 of this gas and pressure 2 of the 2. If we wanted to know the total net pressure of this entire system, if we mix them together, is that this would be a sum of these. And so these are exerting what we call partial pressures, and that again gives us a total pressure of the entire system. So this first equation really isn't anything, like I said, too bad. The one thing you'll see with this formula is that PT, or pressure total, is equal to the sum of your pressures. Now this equation or formula can expand or contract depending on the number of gases in the mix. The more gases you have, we would have to build upon that. If we only had 2, we would have just the sum of 2 gases. So again, this formula can vary depending on what is in the mix. So here, like I just mentioned, scuba tanks are usually a mixture, and this is filled with trimix. As the name implies, that tells us that it's a combined condition of oxygen. It is exerting a pressure of 20 atmospheres, nitrogen has a pressure of 40, and helium is 140 atm. So here it's just asking what is the total pressure. So we can again pick out of the lineup that we have 3 different gases. We have atmospheres of the oxygen, we have the pressure of the nitrogen, and pressure of helium. So there's 3 total gases in this system, being the scuba tank, and it wants to know what is the total pressure. Okay, so we're finding PT is equal to the sum of the pressure of the oxygen plus pressure of the nitrogen plus the pressure of the helium. So then it just becomes a game of subbing in to find total pressure. So we take 20 atmospheres plus 40 atmospheres plus 140. It's not too often that we do much with sig figs with addition. The rule with addition is that it's based on the decimal place. And in this case, we have no decimal place, so it doesn't impact our answer. Everything to the left can stay. So this isn't that this has 1 sig fig, 1 sig fig, and 2. But because we're adding, there are just no decimal places allowed. So 140 plus 40 gives us 180, plus another 20. The total pressure here would be 200 atmospheres of pressure. Okay. Here we have heliox, and kind of like the name implies, it's a breathing mixture. It has oxygen in it and helium. It's prepared for a scuba diver, is going to 200 feet below the ocean surface. At that depth, the diver breathes a gas mixture that is a total pressure of 7 atm. It says if the partial pressure of oxygen in the gas tank at that depth is 1,140 millimeters of mercury, what is the partial pressure in atmospheres of the helium? So from this, we know a couple of different things. We know that total pressure is the 7 atmospheres. And we know that the oxygen is supplying 1,140 millimeters of mercury. Here, it's asking what is the partial pressure. And it also asks in atmospheres of helium. So we know in this combination that the pressure total is equal to the sum of the pressure of the helium plus the pressure of the oxygen. Okay. So one other thing is my total pressure is in atmospheres, my oxygen is in millimeters of mercury, and the problem wants atmospheres. So the most logical thing to kind of begin with here is getting it into a unit that we want, which is going to be requiring the pressure of the oxygen the pressure of the O2 to get converted from 1,140 millimeters of mercury over to ATM. Again, the middle of your sheet has the conversion factors. 1 atmosphere is 760 millimeters of mercury. And let me snag a calculator real quick. Okay, so this has 3 sig figs. We'll keep 3, so 1,140 divided by 760 is going to give us 1.5 atmosphere, which I guess in hindsight that should make sense. So 1.5 ATM. Okay. So now I'm ready to kind of work on the solving of the pressure of the helium. So the total pressure, again, as stated in the problem, was 7.00 ATM. It is the result of the sum of the helium, which is now X, plus the sum of my oxygen of 1.5. So here we're just subtracting X, taking 1.5 from that, it's going to be 5.5 ATM. And so again, this problem and this kind of set, you can see that we found in the first one, what is total pressure? And then the other option is solving for an individual pressure of a gas. Okay. So the next thing is kind of built upon Dalton, and we kind of just lump it in as Dalton's law of partial pressure as well. So oftentimes in chemistry, we need a method to go about collecting gases because, again, they're just going to want to dissipate because they are less dense than the surrounding air, and that they are in the gaseous state. They're moving with lots of kinetic energy, and so they're not going to just stay in a beaker quite like a liquid or a solid. So what we often do is we collect gases by bubbling them through water and trap them into a container. When we collect them, and I'll show you the apparatus setup, there's also some water vapor that builds up in this system. So to know what is the pressure of the gas that you're studying or collecting or working with, you need to know 2 things. So the total pressure of the system is a reflection of the pressure of the gas that you collect plus the pressure of the water. So the little bit of water that changes over to vapor. So we're trying to, again, look and figure out what's the pressure of the gas, again, that you're collecting. So the idea here is that you have zinc reacting with hydrochloric acid. For whatever reason, you're either studying something with the zinc hydrogen reaction, but in whatever it may be, the premise here is you're trying to collect the hydrogen gas. So they have a setup here with a piece of glassware tubing that goes through this stopper that allows and forces all of the hydrogen gas to be forced through this tubing. We then invert, like usually a beaker or some kind of container, over in a tub of water, and that tubing then connects, and this beaker has water, and as more and more of this hydrogen gas is collected, it'll displace that water and force it out, kind of opposite of what you saw in the lab when we burned the candle and the water was forced in. So as the more gas is collected, more and more water will lower. So what we need to do and what we might be trying to study here is what's the pressure of this hydrogen in this system. So there's 2 things that can control that total pressure. So A, the pressure is coming from the collisions of the hydrogen, but there's also some water here. And it's kind of, if you see it, there's a few water molecules here, and then we have hydrogen bumping around too. And so the water is coming from some of this phase changing from the liquid water into the gaseous state. So these 2 things combined give us the total pressure. So here, when you look at these problems, it tells us that a student collects oxygen gas, so that's what we are trying to bubble through, like the hydrogen in that picture, by water displacement at a temperature of 16 degrees Celsius. The total volume is 188 milliliters at a pressure of 692. What is the partial pressure of oxygen collected? Okay, so there's a lot kind of to break down in terms of what information actually is important in looking at this. So right here, it's asking what is the partial pressure of the oxygen. That is based off of this formula here, that total pressure is equal to the sum of the gas. Well, we're trying to collect oxygen, so I'm going to put pressure of oxygen plus the pressure of the water. So here it tells us that it was collected again by water displacement, and it says 16 degrees Celsius. Well, you're looking at this equation and going, this is information I don't need to know. But actually, this is an important thing to notice. What controls how much that water wants to go from the liquid state to water vapor is based on the temperature it's at. So when you look at this pink sheet, there's this big table here at the bottom, and it has a series of different temperatures, and then it gives you a pressure in millimeters of mercury. Okay, so what this is telling you is how much that water is going to exert in terms of pressure based on these different temperatures. And it should make sense, as you go up in temperature, your pressure goes up. So you always get the pressure of the water from your pink table here, and it says water vapor pressure table. So because this was collected at 16 degrees Celsius, we find 16 degrees Celsius on our table here. And that tells us that the pressure of the water is 13.6. And that specifically is 13.6 millimeters of mercury. Okay. So how in the world do we get our missing piece of the pie? Because again, we're solving for the pressure of the oxygen. Okay. So the only thing missing is the total pressure. When you look at this, it tells us that it was collected at a pressure of 692. So unless you have a barometer to tell you the pressure of the room and conditions you're working at, you have no way of knowing the total pressure. Okay, so that typically has to be given to you if you are solving for the pressure of the gas. So I'm going to go ahead and plug in. This is 692. I'm seeing that both of my units of pressure are agreeing. So it's just a matter of plugging in now. So I'm putting in 692 for my total pressure equals, I'm solving for pressure of oxygen, so I'm just going to make that X, plus the pressure of the water. So we can see that this is just a basic step of subtracting here. So 692 minus 13.6 results in 678.4. Now, going back to the rules with sig figs and subtraction, because this doesn't have a decimal, we technically can't keep this, and it doesn't round. So in reality, the answer really should be 678 millimeters of mercury if we're following sig fig rules. Okay. So just another example to again work with this idea of how do we find the pressure of a gas when we're collecting it over water. So here a chemist is collecting a new gas, hydrogen sulfide or H2S. They're collecting it at a temperature of 27 degrees Celsius. So as I mentioned previously, that's an important value even though temperature is not even in the formula. It tells us that the total pressure of the gas that has displaced a volume of 15 milliliters of water. That volume is just extra information. It's not needed. So it's telling us here that the total pressure is 1,555 millimeters of mercury. It asks here at the end, what is the pressure of hydrogen sulfide? So we're solving for the pressure of the gas. So again, what we have here is that the total pressure is the sum of the pressure of the hydrogen sulfide, which is H2S, plus the pressure of water. Total pressure is given to us up above. That's 1,555. And then the pressure of the water is determined through our table because it's dependent on temperature. So at 27 degrees Celsius, we find that the pressure is 26.7 down here at the very bottom. So again, 26.7. And so then what we're finding is the pressure of the H2S. Okay, so I plug in 1,555. I'm going to make pressure of the gas being the hydrogen sulfide X plus the pressure of the water, 26.7. So again, what we're doing here is subtracting. So 1,555 minus 26.7. Again, what we're seeing here is when I solve, I get 1,528.3. This does not have a decimal place. It doesn't matter how many sig figs are to the left of the decimal, but because there's a lack of decimal, we can't keep one. So in reality, our final answer is 1,528 millimeters of mercury if we're keeping rules of sig figs. Okay. So that's kind of Dalton's law of partial pressure. So how you know which one to use, and what I mean by that is, do you use the table with water? Do you not use water? Is if it mentions anything about water and water displacement. Okay, so here this key word in this problem was that it was displaced. Okay, so that tells me that I'm working with the pressure total is the sum of the gas plus the pressure of water. Same thing here. The key word is it mentioned water displacement. If you look back at the previous examples prior to that, it doesn't mention anything being collected by displacement. It doesn't talk about anything with water. So that is how you know the difference between those two formulas. Okay. So the next law we're going to look at today, besides Dalton, is Graham's law. So gases, and we're going to show a visual representation through a lab where you're going to observe the rate of effusion of three different gases. So effusion is basically the rate at which it's moving. So effusion and diffusion are not quite the same thing. So effusion is like something is evaporating and it's naturally changing over. Say you have like a spritz of perfume. And so effusion is when those gas molecules that is the perfume carry their way throughout the whole space and you can start to smell somebody's perfume on the other side of the room. Diffusion, again, is kind of through an opening. So like if you pop a hole in a balloon. So I kind of use these two words interchangeably, but it's basically we're looking at how fast do different gas molecules move. So we're looking at velocity, and the things that decide how fast or slow a gas is going to move is, guess what? Their molar mass. And I'm sure this is going to be groundbreaking. Lighter molecules move faster than heavier molecules. Okay. So Graham's law looks at the rate of effusion, so the rate at which they are moving when they're kept at the same temperature. And we look at the square root of their molar mass to then figure that out. So on your pink sheet, I didn't have a spot for your formula in the notes for some reason. This is the law that we're using here, where rate of effusion A over rate of effusion B, where A represents one of your gases and B represents another one of your gases. So you substitute in based on what you're comparing. And here it's equal to the square root of the molar mass of B over the square root of the molar mass of A. So we're going to look at examples here. So it's asking us here to compare the rates of effusion of hydrogen and oxygen at the same temperature and pressure. So you'll notice that there was not even a single number given to you in this problem. What we need to do first is we need to find the molar mass of each of these substances, hydrogen and oxygen. So hydrogen chemically is H2 and oxygen is O2 because they're diatomics. So with using our periodic table and the understanding of them being diatomic, hydrogen's molar mass is 2 grams per mole. And oxygen is going to be 32 grams a mole. And it's wanting us to compare the rate of effusion. So when it asks us to compare the rate of effusion, we are essentially solving for this side of the equation. We have everything we need for this left-hand side. So again, it'll make more sense as we take a look at it. Now, when it comes to deciding which gas to use as A and which gas to use as B, it's not based on the order they're given to you in the problem. What you want to use to decide that is you always make A the lighter gas and B is going to be your heavier gas. Well, hydrogen is definitely much lighter, so we're going to assign this as A in our formula. And oxygen has a heavier molar mass, therefore I'm going to make this B. So I'm just going to put rate instead of writing this all out because I know how much you guys want to. We're going to just write this as rate is equal to. And so I'm going to go ahead and just write this formula out where it's the square root of molar mass of B. But instead of writing B, I'm going to swap that out with the chemical formula of oxygen over the square root of the molar mass of A, which is the light gas, which is hydrogen. Okay. So what we're doing is essentially comparing how much faster would oxygen move, or I should say hydrogen move, compared to oxygen. So substituting in my information now, I have the square root of 32 over the square root of 2. So we're going to go ahead and swap these over to decimal forms. So I'm going to go ahead and find that. So second square root 32. I got to get this out of math print mode and put it back in decimal form. Just make sure that's really what I want. Yeah. Okay. So it looks like we can say we'll just go 5.66. Over the square root of 2, which simplifies down to 1.41. And then the last step in simplifying this is through division. 5.66 divided by 1.41 gives me an answer of like 4.01. Okay, units. Units canceled here. What we're doing with this law is we're looking at how much faster is hydrogen going to move, because hydrogen is the light gas. If you look back at our formula, it says rate of A over rate of B. We essentially solved for this entire side of the equation. So this is saying that 4.01 of A is to the rate of, and we could just substitute this in as 1 of B. So what this is saying is when you get your answer here, this is telling you how much faster the light gas, hydrogen, is moving compared to the heavy gas, oxygen. So our answer here, we actually write out kind of a short statement that hydrogen effuses basically 4.01 times faster than oxygen. And it's all because hydrogen is a much lighter gas, therefore is going to move much faster, specifically 4.01 times faster than oxygen because of their relative molar masses. Okay? So this next one is a little bit different in setup. It says a sample of hydrogen effuses through a porous container about 9 times faster than an unknown gas. Estimate the molar mass of the unknown gas. Well, we know one of the substances is hydrogen. Therefore, we know the molar mass of hydrogen as 2. It also tells us the rate. It tells us that hydrogen moves 9 times faster. If hydrogen's moving 9 times faster, hydrogen is much lighter than the unknown material. So the ratio here is 9 to 1. What we're trying to find is the molar mass of some gas. We don't know what it is. Okay. So when we go to set this up, looking at our formula, you have to keep track of what is A and what is B. A is the lighter gas. Okay. So A is going to be hydrogen. So this is my molar mass of A. And this is the speed of A, because hydrogen, again, was moving faster than the unknown gas. So when it looks at rate of effusion of A, I'm going to plug in a 9, because it's moving at a ratio of 9 times faster to a ratio of 1. There's no unit there, okay? From there, I know that my equation is an inverse here. It says it's the square root of molar mass of B. I don't know what B is. That is my X, okay? Over the square root of A, which was the 2 grams, okay? So now it becomes a breakdown of doing some algebra, some different algebra than we've done, but we're still cross multiplying, okay? So when I simplify this, I end up with the square root of the molar mass of X is equal to 9 times the square root of 2, okay? And this is grams per mole. And I got a little lazy here. Okay, so I'm going to go ahead and work on calculating that. So I'm going to go ahead and take the square root of 2, and I'm going to multiply it by 9. And we get that m of x, molar mass of x, is equal to, we'll go with 12 grams per mole. Okay. So how do we work on getting x by itself? Well, we need to get the square root gone, and we do that by squaring. So the molar mass of our unknown gas is just going to be 12 squared, 144. So this formula, I would say, is probably the one that students struggle with the most. So looking and comparing real quick. When we look at the previous example, in the prior example, you were just finding the rate of effusion. Rate of effusion means you're solving for the entire kind of left-hand side of the equation. You know the identity of the two gases you're comparing, and you find their molar masses. A is always the light gas, B is always the heavier gas. So in setting it up that way, we end up putting the molar mass of the heavier gas in the numerator, molar mass of the lighter gas in the bottom. That tells us how much faster the lighter gas moves to the heavier gas. In this problem, we had the rate of effusion. We had that it was a 9 times faster, 9-to-1 ratio. And we were trying to find the molar mass of one of the two gases. So again, your ratio will always be, this could have been 30-to-1, but it will always be whatever given number, it's always compared to 1. We then know that the unknown gas was the heavier gas and hydrogen was the light gas. Again, through working out my cross multiply and divide, the sig figs get a little bit weird here. Kind of just do your best to estimate if you want to just do whole numbers. I'm not going to be too picky with sig figs. Okay? Feel free to reach out with questions.